Chapter 3.4, Linear Programming. From this video, you should learn to solve problems using linear programming. There are 4 vocabulary words that you really need to know before we start this lesson. The first is constraints. Constraints are just limits on your system. I'm going to write just limits. Linear programming is another thing you may not know what it means. What it is a method for finding a minimum or a maximum value of some quantity. The next is a feasible region. The feasible region contains all the points that satisfy all the limits or the constraints. And then finally you have the objective function. That's the quantity that you're trying to maximize or minimize. You model it with that objective function. Very important thing for linear programming. It's not going to make a whole lot of sense until you use it, but if there is a maximum or minimum value of the linear objective function, it occurs at one or more vertices of the feasible region. So the feasible region is going to be created by 2 axes, the x and y axis, plus your 2 lines. So it's going to create like a little shape in there. And at one of those vertices, that's going to be your minimum or maximum value. Okay, the first thing we're going to do is test vertices. For this one, you have 4 constraints. If you graph them on the XY coordinate plane, the bottom 2 constraints are going to be your axes. X is greater than 0. That is actually going to be the x-axis. So it's greater than, so we're going to shade above that in pink. A lot of shading going on here. The last one is y is greater than or equal to 0. So yeah, that's actually going to be the y-axis, and it's greater than, so you're going to shade all the y's that are greater, which is to the right. Okay, and then let's deal with our 2 lines. This is very similar to the last lesson. What you're going to do is put it in slope-intercept form. I'm going to choose another color, so we'll do purple. We'll move the x over, and we get 2y less than or equal to negative x plus 5. Divide by 2. So we get y is less than or equal to negative 1/2 x plus 5/2. So we want to graph that. 5/2 is your y-intercept. So you're actually going to go up 5/2, which is 2.5, and put a point. And your slope is down 1, right 2. And then down 1, right 2. And that's going to be a solid line. And it's less than or equal to, so we're going to shade below that line. And you're starting to see this little region form right there in the middle. But now we have one more line we have to graph, and that's that x minus y is less than or equal to 2. So we're going to put that in slope-intercept form. We get negative y less than or equal to negative x plus 2. So positive y must be greater than or equal to positive x minus 2. So my y-intercept is going to be negative 2, put a point. Slope is positive 1 over 1, up 1 over 1, up 1 over 1. And I see this line. And I'm going to shade above that, so I'm going to shade in here. Now it's starting to really cover up where my feasible region is, but I'm going to outline it again in black. So it goes down here, right to here. This is where it's shaded 4 times and over. So I need 4 vertices. The first one's going to be 0, 0. And a vertice is just like the corner here. So here's my next vertice. That's 2, 0. Then here's my next one, so that's 3, 1. And then my last one is up here, and that's actually going to be 0 and then 5/2 or 0 and 2.5. And that's where all these points down here actually came from. And what they want to do is say which one maximizes P for the objective function. So now that I have those 4 points, I'm going to plug them in for P, and P is this function right here. So I'm going to plug in X and Y for each one. So the first point, let's do 0, 0. That's probably going to minimize it, not maximize it, because the numbers are so small. So that's going to be 2 times 0 plus 0, which is 0. The next one, let's do 3, 1. That's going to be 2 times 3 plus 1, which is 5. So I tried this one. Let's do 2, 0. You always want to try the hard one last, so we'll save the decimal for last. That's going to be 2 times 2 plus 0, so that's 4. And then the decimal is going to be 0, 2.5. So that's going to be 2 times 0 plus 2.5, and that equals 2.5. So whichever one of those is the highest, which is 3, 1, is the answer. So C. Okay, use the constraints from example 1 with the objective function P equals X plus 3Y. They want to know which one maximizes P. So we're going to use that function again, and we're going to use the same 4 points. If you don't remember, the points were 2, 0, 0, 0, 3, 1, and 0, 2.5. You don't actually have to graph these if they give you the vertices, or if they give you the the vertices of the feasible region. You don't have to graph it because you already have the vertices. I just did that to show you what to do. Okay, so we're going to plug in each one of them. I would probably just start with the easy one, so 0, 0. That's going to be 0 plus 3 times 0, which is 0. Let's do 2, 0. So that's going to be 2 plus 3 times 0, which is 2. 3, 1 is going to be 3 plus 2 times 1, which is 5. And then 0, 2.5 is going to be 0 plus 3 times 2.5, which is 7.5. So in this case, D is the answer because that gave me the highest number. This is the point in the video where you show your work. I want you to graph these 3 constraints on a graph. I want you to name the vertices, so the corners that the feasible region creates, and that's it. You don't have to maximize or minimize anything. Just graph the 3 constraints on a graph and name the vertices of the feasible region.